Hi, Assalamualaikum and good morning, good afternoon all. Uh, good morning all. Good day everyone. Welcome to OTC Asia live session. My name is Sharini Mokhtar. I am the General Manager in the Resource Development and Management, Peninsula Malaysia, with the Malaysia Petroleum Management in Petronas. And I am the moderator for today's University R&D showcase. In this session, Daniel Chong from University of Nottingham will share a presentation on integrated simulation optimization strategy of triethylene glycol natural gas reaction system. Triethylene glycol, aka TEG system, is a crucial deaeration system, especially for offshore gas supply to meet the sales gas specification per the contractual GSA or gas sales agreement, as well as to ensure the downstream facilities, such as the main gas pipeline and the onshore receiving facilities, is able to further handle the sales gas prior to sending the treated gas to our gas processing plant or LNG plants. By meeting the dehydrated or dew point gas spec, we will also save on the capital and OPEX costs in form of material selection for the downstream facilities from expensive corrosion-resistant alloy or exotic materials versus carbon steel. In Malaysia, security of gas supply to the domestic, power, LNG, and others are critical, especially today there is an increase in the gas demand in the market. Thus, though TEG is only one part of the gas processing system on onshore facilities, it plays significant role as one of the hard or critical equipment for the onshore platform to enable the sales of gas to the market. Since my current position as the resource owner in managing the Peninsula Malaysia oil and gas development, this topic is close to my heart in making sure we have the optimum facilities design and life cycle costs to deliver the hydrocarbon to the market and the buyers, where in Peninsula Malaysia the gas is crucial for sustainability of electricity supply of our day-to-day life. Gas is a cleaner source of energy compared to coal. Of course, there are alternative dehydration systems to be explored in the market as well. But today, let's hear on the TEG and the integrated simulation optimization strategy studies as conducted by Daniel. Let me introduce Daniel. Daniel is a final year chemical engineering student from the University of Nottingham. He had collaborated this work together with his academic supervisor, Professor IR Dr. Dominic Fu, and industrial supervisor Dr. Zulfan Adi Putra as part of his final year project. I encourage the audience to submit your questions and comment throughout the presentation, and we'll be addressing those questions during the live Q&A. Without further ado, I invite Daniel to the stage to begin his presentation. Thank you.
Good day, OTC Asia. I'm Daniel, a final year chemical and environmental engineering student from the University of Nottingham, Malaysia. I would like to present my topic on simulation and optimization for triethylene glycol dehydration system for natural gas processing. In this presentation, I will cover the introduction, process description, methodology, development of non-linear regression models, development of optimization model before the work is concluded. The natural gas treatment process is to produce pipeline quality gas specifications. There is a series of natural gas processing steps which are required for treating raw gas. It begins with inlet separation, acid gas removal, gas dehydration, hydrocarbon dew point controlling, nitrogen rejection, helium recovery, and ends with gas compression before transmitted and distributed to the natural gas grid. We will be studying on the glycol dehydration system in the natural gas processing facility. In this work, we will be focusing on the simulation and optimization techniques and the method to conduct regression analysis that could be not only used in natural gas dehydration processes but also be applied in any offshore and onshore platform processes. There will be three operating parameters, which are the overhead reboiler temperature of the regenerator, the flow ratio of the water-rich stream, drizzle hydrocarbon solvent flow rate, and the studied responses are the reboiler duty, hot oil duty, condenser duty, pump duty, TEG loss, CO2 emission flow, and water content in the dry natural gas. So first of all, wet natural gas is fed into the glycol contactor from the bottom and lean glycol from the top. The lean glycol is a liquid dehydrating agent to absorb water from the wet natural gas. The top product is the dry natural gas, whereas the bottom is the TEG rich in water. In the glycol contactor, the pressure and temperature is set to 70 bar gauge and 30 degrees Celsius to enhance the absorption efficiency of water. The rich glycol is then depressurized to atmospheric pressure and heated so that water along with hydrocarbons can be evaporated to the overhead of the regenerator column. First, we will begin talking about the overhead flow before explaining the bottom of the regenerator. Drizzle hydrocarbon solvent is added with the overhead product and is fed to a separator, where light components will be liberated from the system. Then, since hydrocarbon is immiscible in water, they are fed to a three-phase separator. The water-rich stream will either be recycled back to the regenerator or being removed from the system. Most of the glycol will lost to this outlet stream along with water. And going back to the three-phase separator, the hydrocarbon-rich stream will pass to the hot oil duty to be vaporized and is later fed to a stripping column. The lean glycol from the regenerator here still contains a minor amount of water, so it is further sent from the stripping column for further water removal. This addition of hydrocarbon solvent and the stripping column are the main characteristics of the drizzle process, which differentiates itself from other technologies. And after that, the bottom product will be recycled back to the initial glycol contactor to absorb water, and the process is repeated. So firstly, we will develop a base case simulation model using Aspen HYSYS. The design is based on operating parameters and specifications of the studied plant. We will use the sensitivity-based case study function from HYSYS. HYSYS built-in optimizer is not recommended because it only applies gradient-based algorithms, which requires convex models to generate the local optimal values. And after obtaining the data, we export it to Excel spreadsheet to develop the surface plots and contour plots to study the effect of the independent variables on the responses. So here is the simulation model developed based on the process flow diagram provided by the industrial supervisor. The base case values must be comparable to the plant data before proceeding to the next step. Next, we will move on to the case study using HYSYS. Based on the results produced by the case study, we can develop surface plots for each responses. For example, we can see that when the reboiler temperature and solvent flow rate increases, the reboiler duty shown in the upper left screen increases, whereas hot oil, condenser, and pump duty decreases substantially. Besides that, TEG losses and CO2 emission increase, and the natural gas will have a better dehydrating performance with increasing temperature. The last figure with y-axis as the operating cost, it can be observed that optimum cost hovers around low temperature and low solvent regions. Next, the regression model equations for each response will be developed. The responses are a function of reboiler temperature, flow ratio, and solvent flow rate. The responses are applied in the regression model equations, which is QR, the reboiler duty, and subsequently is the hot oil duty, pump duty, triethylene glycol makeup flow, carbon emission flow rate, and water content in the sales gas. I will demonstrate the method to develop a non-linear regression model using Excel. The list of data was extracted from HYSYS case study table. Even though Excel has a regression add-on function, it is only applicable to linear regression. So I have manually powered the input variables and studied the interactive effects between input variables to develop the non-linear regression model using Excel. Excel was able to conveniently show many statistical data as well as the coefficient constant for us to study each of the input variables. So I was able to get the equations that represent each response variables. Using the add-on function provided by Excel, we are able to devise the nonlinear regression model. For example, we can find the coefficient constants for each term in the condenser duty. Finally, Lingo programming language is used to develop the optimization model to minimize the operating cost of the plant. The nonlinear equations will also be included in the optimization model. And in this slide, these are the constants and specifications of the simulation and plant model. It is important to add on these terms in the Lingo optimization model so that optimized operating parameters will not go beyond the plant's capacity to reduce the tendency of poor estimations from the model. The last step of the work is data validation. It will be done by comparing values generated from both HiSys simulation model and Lingo optimization model. Based on the summary of validation for the response parameters, all nonlinear regression equations were obtained with a low error of less than 1%. However, there is a 2.15% error in the pump power. This is due to the sensitivity issues caused by high number of recycle loops in the Aspen HiSys simulation model. Hence, the accuracy of the simulation model has to be traded off so that the model can be converged. Looking from the base case model and the optimized model, the final results show that operating cost of the TEG makeup flow had decreased substantially, whereas other responses such as utility costs involving boiler duty, hot oil exchanger, condenser duty and pump duty has minor changes from the base case. The optimized configuration has reduced the hourly operating cost by $40.62, which is to $76.63. In conclusion, the nonlinear regression analysis generated R-square values of more than 99% for each response parameter. The integrated simulation and optimization approach was fairly accurate with a maximum error of 2.15%. Process evaluation optimization performed was able to minimize the operating cost of the base case by 34.6% from $938,000 to $613. Before I end my presentation, I would like to emphasize that the simulation and optimization approach can not only be used in dehydration process, as it can be applied in any chemical engineering related production industry, as it can give a good predictive of optimum values without any actual run of the plant. Finally, I hope you will be interested in my presentation topic. Thank you.
Okay, thank you, Daniel, for the great presentation. Very technical indeed with all the formulas and calculation. I barely remember my days as chemical engineering student in those days in my life. So thank you for that. So let's take up the question. Are you ready, Daniel? How are you, by the way, today?
Yes, I'm ready and I'm able to take out any questions that is asked the floor.
Okay, we'll
Yes.
start with the first question. The first one, talking about the presentation that you just shared, could this methodology or simulation tool be potentially used as a quick troubleshooting tool to solve operational issues and propose the resolution plans using this tool? Thank you.
Okay. For that question, my answer will be yes and no, because the no part is because that we need more details such as the specifications of equipment, the flow rate, temperature, and other operating conditions of the system in order to generate a accurate simulation model for the process system. But however, once the process system is constructed, and besides that, we after constructing the software model, since it's actually a virtual model, we need to have validation data sets from the actual plant in order to compare each of the errors that we had got from the software. And after overcoming this section, only we'll be able to generate the correct base case model for that process. And after that, we only able to get the responses from the case study of the simulation software, and also to understand the interactive effects of, for example, the input parameters such as the temperature, in my case, the flow ratio, the solvent flow rate and all that, on the reboiler duty and the pump duty and other utility, which will in the end will be translated into operating costs with the help of the lingo optimization model, as mentioned. And the answer, because I say previously I said no, right? Because it actually takes quite a long time for me to actually get a good base case model with low errors. And yeah, and also another 2 to 3 weeks in order to get the optimization model developed. I said actually to develop the coding of the lingo model in order to optimize the operating cost. Yeah, that
Okay,
is.
thank you so much, Daniel. Going to the next question, the reduction in OPEX as shown in your study is quite high, about 30%. What are the basis assumption that you use or considered when you calculate the operating costs?
Okay, so firstly, I've assumed that the I did not take into consideration of the maintenance costs, the salary or the fringe benefits of the workers, since the number of equipments and the process are almost the same. And because assuming too many things inside the actual plant will also result in further inaccuracies or errors. And besides that, I have also omitted the capital costs, since my objective here is actually to reduce the operating cost of the existing plant, which has been operating for quite some time in the offshore platform. And I also did not consider the profits of the gas because it is also fluctuating from time to time, and it's also not very sensible to calculate them. So in the end, I only calculate the operating costs involving utility and the raw materials and the carbon CO2 emissions. And that's it, because there are also many other processes after this glycol dehydration process. So yeah, I did not calculate the profits and all that.
Okay, so basically you're focusing on the system itself.
Yeah.
Okay, so the next question, how do you ensure that the TEG is working efficiently where the water dew point specs are met, meaning that there is no hydrate permission, no water dropout within the main gas pipeline operating envelope to protect the export pipeline and the onshore receiving facilities?
Mm, the water dew point and the water content in the sales natural gas is actually determined by the Energy Commission, and each depending on the different climate. For example, in Nigeria, their water content specification will be twice as much as compared to Europe, because Europe is in a colder climate. And for Malaysia, the water dew point specification is at negative 25 degrees Celsius. But in my work, the supervisor had requested to set the dew point up to negative 50 degrees Celsius, because the process of the triethylene glycol dehydration process is involving an enhanced dehydration process, which is called a drizzle TEG dehydration, and which is much more efficient compared to other conventional dehydrating processes. And since I'm only doing the modeling, and to ensure that the pipelines are omitted from hydrate formations and the specifications are met, actually, one thing we are able to do is to add a safety factor of 2 to 3 to 5 degrees Celsius below the minimum water dew point specifications. And another performance indicator would be also by taking sample data tests from the regenerated TEG to ensure that the water content and the purity of the TEG is satisfied. So because the TEG is like it's like a clot to remove water from the natural gas. So the drier or the purer the TEG, the better the removal water efficiency it gets. I hope that I answer your question.
Yeah, thank you so much, Daniel. That's the question from the audience. I'm moving on to the next question. How would this simulation optimization tool that you are doing now beneficial, and what is the potential application to the oil and gas industry?
Sorry, what's the question again? Can you rephrase it?
Okay, how is the simulation and optimization tool beneficial, and what is the potential application to the oil and gas industry?
Oh, so it is beneficial since the simulation and optimization model can be applied in most process industry. Since HYSYS Icon SuperPro Designer could be used for simulation too. And for optimization, we could also use Python, MATLAB, or even like the one I use is Lingo. And the as long as we are able to know the detailed specifications of the studied plan, we are able to simulate and optimize it correctly. And also, I would like to emphasize that, and probably in designing the new offshore process, we are able to use the simulation software and tool to able to get the optimized values in order to purchase the equipments which is within the specifications in order to save the capital or also the operating costs. And also for my existing plant, right? Uh, Example here is like in common sense, we would not know that increasing the reboiler temperature would in turn reduce the operating cost of the entire plant. But using this simulation optimization tool, we know that actually increasing the temperature would reduce the losses of the TEG flow. So in turn, it will be is like a trade-off between utility costs and the raw material costs. And in this studied plan, it works out that the increasing of the utility costs will able to save much more money for the plant. Yeah, that is my answer for that.
Okay. I'm not sure whether we have the time for another question. Maybe we'll try. We noted on your TEG system, but what would be alternative dehydration system which to TEG which could deliver this spec as what you mentioned just now, that can manage a lower OPEX and maintenance costs?
They are in the oil and gas industry. There are other types of technology for removal of water from the natural gas, such as for me here, I'm using drizzle TEG removal. There are also stripping gas technology, vacuum TEG removal, glycol dehydration system, cold finger technology, and other adsorption processes where they are using activated alumina or silica gel to pressurize and depressurize the absorption column to absorb and to remove the water subsequently. And for the conventional part, they are normally using stripping gas column, and such as they are using nitrogen gas, inert nitrogen gas, or instead of and also using natural gas, but it is also a single pass system, so it will be quite environmental harmful to the it will be quite harmful to the environment. Yes.
Okay. Thank you so much, Daniel. I guess that's all the time that we have for the question. Um, Basically, it's a very interesting topic to me, especially as you hear at the start. I'm managing the supply of gas to Peninsula Malaysia, where we depend on the gas for our power that we use day to day. We don't want blackout, right? So
Yes.
anyway, and I hope the from the assessment that you're doing in terms of your R&D, maybe you can look further in terms of how to make sure the system can go into the managing the hydrate formation and water dew point properly, so that the system can be fully efficient and lower cost. So with that, I would like to thank everyone for joining today's session and interacting with us. I really appreciate the opportunity to learn more from this session, and I hope the participants, the audience, will also be able to learn from this session as well. With that, thank you and enjoy SP Asia, OTC Asia, which will be coming next week. Thank you.
Yes. Thank you,
Bye.
Parini, for moderating. Thank you.